Today we're going to talk about support vector machines. Support vector machines are kind of like an upgrade and generalization of the perceptron. So there's two parts. In the first lecture, we're going to talk about hard margin support vector machines, which are relatively close to perceptron, but we'll see how it's an improvement on that. And then the next lecture, we'll talk about soft margin support vector machines, which are a refinement and a generalization of hard margin support vector machines. So you can see that each of these is going to build on the previous one. So let's talk about what sort of setup we're going to have here. Well, we're going to be talking again about a classification problem where we have points x, y, where these are in R to the D. So similar as before, we have feature vectors which are d-dimensional, and the labels are going to be plus or minus 1. So this is exactly the same type of setup we had for perceptron, and in particular for this part, when we're talking about hard margin SVMs, we're going to be using the assumption that the data is linearly separable. And I mean the training data set. So it's linearly separable. Now, if you don't remember what that means, let's draw a picture of what that means. It means something like the following. So imagine we have, we don't really need a coordinate axis, I guess. Let me just draw some points. So the linearly separable essentially means something like we're going to have some points over here, which all have one label. And there's going to be some points over here which have another label. And the idea is linearly separable means that there's some line we can draw between the two different classes, or perhaps in a higher dimensional, a plane that we can draw which separates the two different classes. That is, all the plus ones are going to be on one side and all the minus ones are going to be on the other side. Now recall what perceptron guaranteed. It basically said that any point, it essentially said it would find any line which separates the two. So for example, it could, for example, find this separating hyperplane, or it could find this separating hyperplane, or so on, anything in the middle as well. Now, which one's the best? Intuitively, you might think that this one is not as good as this one. This one, in some sense, feels the best, just because it seems to separate the two classes the most. It somehow feels the most accurate, but perceptron, again, doesn't care. It might not find this. It might find something more like this or something very close, which might be bad in terms of generalization properties. For example, if you got a bit more data, maybe you would have something that falls over on this side, and that would indeed be an incorrect prediction. It would be predicted as a -1. So to try to basically adjust for issues like this, the sort of, in a formal sense that we're going to try to formalize today, the kind of best solution is going to be something like this, something which is the furthest away from both of the classes, in order to, perhaps one interpretation is minimize the chance that if you saw more data that it would cross over the line. Maybe we get something like this. So right, that's essentially what the support vector machine, the hard margin support vector machine solution, or SVM as it's called, hard margin SVM, is going to try to do. It's going to try to find the perceptron solution, that is the separating hyperplane, which additionally maximizes the distance to both of the classes. Now, this is a bit informal, because what does it mean to maximize the distance? Well, let's recall some of the notation we used in the previous lectures. So the important thing is the concept of the margin, or rather the distance of a point to the hyperplane here. So suppose we have a hyperplane, or a separating hyperplane, which is defined as follows with sort of parameters, let's say, with parameters, let's say w prime and b. I'm going to just use these, and b prime. We'll use these primes for reasons that'll be clear in a minute. So this is our solution. Remember that our hyperplane is basically defined, it's defined by these two parameters. And essentially, the distance from a point to the hyperplane. So let me write this: dist from xi to hyperplane. This is going to be, there's a following expression, which is sort of classic geometry. Maybe you learned this before, which is gamma I. We're going to use this for the distance of point, for this part of the lecture at least, we're going to use gamma I for the distance from point I to the hyperplane. And it can be written essentially like this. The inner product of w prime xi plus b prime, and I guess the absolute value of this. Maybe you can just throw in yi for the points which are correctly classified. So yeah, let's just pretend we found a solution and everything's correctly classified. Then the distance is just going to be this value, where we have that the magnitude of w prime, it has to be normalized to be equal to 1. So if you do it like this and you rescale or normalize your solution so that the magnitude of the sort of normal vector of the hyperplane, which defines the hyperplane, if you normalize it so that this is 1, recall that you can always scale it up or down, but we're always going to look at the normalization, which makes sure it's equal to 1. Then this is going to be the distance. Essentially, let me kind of try to draw it for you. For example, the gamma for this point in particular would be this magnitude. Oh, that's an ugly pink, but we'll stick with it. Basically the distance from this point to this plane, and yeah, it's just going to be this magnitude right here is equal to this. Let me just get rid of that because that hurts my eyes. Okay, so that is the distance for a point, between a point and the hyperplane. Now, the idea of the SVM solution, like I said before, is it's going to be like a perceptron, but trying to maximize the margin. That is, what is the margin? Let's say what the margin is first, just to recall. The margin is, assuming all the points are classified correctly, I guess you can say it's going to be, the margin is going to be the min over all points of gamma I. So this is the margin. Perhaps fittingly written in the margin. So yeah, essentially, it's going to be essentially the closest point. So for this data set in particular, then the margin would be realized by this point, because it's going to be the minimum distance between the point and the line. Of course, this is much larger. And so the goal of SVM is essentially, let me write it informally first, and then we'll write it as a formal optimization problem. So the goal is to maximize over, say, W, and I guess W prime and B prime. We're trying to maximize over all of the parameters for the solution, the minimum of the distance. So this maximizes the margin. This is essentially what a SVM tries to do. So let me actually write this a little bit more precisely as to what exactly the SVM solution is and how it corresponds to this this goal to maximize the margin. So I'm going to write it in a way that is less common first, and perhaps for we'll see why at first, and then we'll translate it to the more common version of the optimization problem. So the goal is to the following, like I said, maximize over all W prime and B prime some gamma, where we have the following constraints. Like I said, we first of all require that the L2 norm of W prime is going to equal 1, because that's then that's kind of the normalization we'll look at for making sure this gamma I represents a distance, the distance. And we also have the following constraint, which essentially says that everything is has a margin at least gamma. So, okay, this is the SVM optimization problem in a less common form. We're going to reword it in a bit to write in a more common form, but let's just, again, look at what this wants to do. So what this says is that we're trying to make sure that if you put each point into this linear, into this sort of linear classifier, kind of like a very perceptron style classifier. In fact, it's exactly a perceptron style classifier. You just take the inner product with the parameter vector, add on some bias, and multiply it by the sign. So essentially, you just take whatever perceptron style linear classifier that you have, and you need that for all points in your training data set, that the distance from the point to the hyperplane is going to be greater than or equal to some value gamma. And then you try to maximize that value gamma. So in other words, this is going to try to maximize the margin, because this is kind of going to be realized. The margin is going to be realized by whichever I causes the distance to be minimum. So it's trying to make sure that all of the points are at least gamma. So yeah, this is essentially just trying to match this intuition of trying to maximize the margin. Now, like I said, this is not a very common way of doing this problem, and of stating the SVM problem. And the reason is that this is kind of weird because you have to look over. It's not clear how to deal with this type of constraint where you have to always deal with the normalized W prime. And yeah, there's a simpler way to write it, which essentially eliminates one of the parameters gamma. And the way we are going to do this is we're going to perform a substitution in this following sense. So let me separate this. So let's substitute. We're going to substitute that W is equal to W prime is equal to gamma times W, and B prime is equal to gamma times B. The idea is that I want to try to rescale these. So somehow I want to get the gamma and the weight vector W kind of rescaled appropriately. So if we do this, then there's some things which are easy to derive. For example, then this implies that gamma is equal to okay, let's do it step by step. So one thing we can say is, first of all, we'll have just substituting some of this in. We're trying to maximize over now gamma times W, gamma times B of gamma. This doesn't change. And we have the following. So the first thing we're going to do is substitute in this constraint here into this one here. And so this will give that the magnitude of W, L2 norm, is equal to 1 over gamma. Just substituting this into this second constraint, or the first constraint, I guess. And the other constraint we're going to have is the following, just substituting in both W prime and B prime in here. Then we have that yi, inner product of gamma W comma xi plus gamma times B is greater than or equal to gamma. And so what we can do actually is just divide the whole thing through by this gamma factor. And what will that give us? Well, this is a big eraser. All right, well, too bad. If we just do this rescaling by gamma, then we will in fact have this. So in other words, we have now basically gotten rid of the gamma and in almost everywhere, and we've just replaced it with 1 here. And in fact, this can be simplified a little bit more. So now you'll notice that there's not really any important role of the gamma, in the sense that we're maximizing gamma, where gamma is equal, 1 over gamma is equal to the L2 norm of the parameter vector. So let me just do a bit more of a simplification here. So what we're going to do is essentially just do a substitution. Since we know that the L2 norm of W is going to be equal to 1 over gamma, then we can just substitute in gamma equals 1 over the L2 norm of W. Okay, I'll do this in 2 steps. The first step we'll do is just eliminating this constraint by substituting it in right here. So maximize over gamma w, gamma b, and this becomes 1 over the L2 norm of w. And we have these constraints. And the final thing to arrive at the final problem we're going to do is just notice now that gamma doesn't appear anywhere in this, so we can just like maximize over just w and b. And the second thing we can do is if we flip this from, instead of maximizing 1 over w, the norm of w squared, or sorry, instead of maximizing 1 over the norm of w, then we can minimize just the norm of w, because it's just going to be essentially the same thing. And we'll also put a constant in front of that. So just for rescaling, which looks nicer and is more common. So that gives us the following. If we do both of those things, that gives us the following. We're now trying to write the final SVM problem, which is minimize over all w and b 1/2 of the L2 norm of w squared. Again, since it's a monotone function, this doesn't make any difference, but this is often a more convenient representation. And we have the constraint that such that we want yi times the sort of classification plus b is greater than or equal to 1. So this is, at long last, it took a little while for us to get here, but this is essentially the hard margin SVM problem. So now let's take a look at it and try to compare it with what we had before. So again, what we had before, I think, is this is perhaps the more intuitive way when you first learn about it. It essentially just tries to maximize, it explicitly tries to maximize the margin such that every point's distance to the line is greater than some margin. And we have a normalized parameter vector, or a normalized, yeah, the parameter vector of the hyperplane is normalized. So this makes sure that, essentially this makes sure that the magnitude of the parameter vector is 1. But one way of seeing what we did is instead, we're trying to say, what if we fix gamma to be 1 and see how, and instead try to optimize the parameter vector in terms of its magnitude. So that's all we really did. We changed the perspective from keeping the norm of w fixed to keeping the norm of gamma fixed and rescaling the parameter vector. And this is, if you go through follow these steps, that's essentially just rewriting the problem in this way. And this is convenient to do it in this way because we don't have to deal with this gamma parameter. Yeah, this is a nicer thing to optimize, in my opinion. Right. Okay, so that is the objective. Let me just note a few things. I'm just going to introduce some notation which we'll use throughout this lecture as well as the next one. Which is essentially saying this term here, this whole term here, this expression, this is going to be yi hat. Yeah, I'll write this here. Yi hat is equal to wxi, comma, or plus b. And this is essentially how we use it as a prediction. Whenever we're doing a prediction, suppose you have trained some sort of hard margin SVM, very similar to before with perceptron, you're going to use the prediction will be sine of y hat I. You just do the linear classification, and then if it's greater than 1, then you pick that it's, or sorry, if it's greater than 0, then you pick that it's going to be a +1 classified. If it's on the other hand, it could be -1 classified. Cool, so that's how you use this. Let me talk a bit about, let's compare this also with the perceptron. So the perceptron algorithm has the following, here's a kind of odd way to write the perceptron objective function, the perceptron optimization problem. One way of writing it is the following. Okay, and I'm going to use this little bit of notation. So essentially, this is the exact same thing as we had before. So let me just say CF compare with perceptron. Blah, blah, blah. Okay, I'm not gonna write it all. But yeah, the perceptron is essentially, sorry, I guess someone might be trying to read this, so let me just try to write this a little bit cleaner, I guess. So compare with the perceptron. Then this is the optimization problem that we're trying to solve. So just compare the perceptron with the hard margin SVM solution. It's essentially the same constraints, but the interesting thing is in the perceptron, we didn't try to really optimize anything. We just want anything which satisfies these constraints. But here, we essentially try to find the solution which minimizes the L2 norm of the solution parameter vector. Now this might actually, so this can be seen as kind of a refinement in some way. It's a refinement of this problem in the sense that we do all the same things as before, but now we have an additional objective, and any solution to this will also be a solution to the perceptron problem if one exists. Again, remember crucially for this part that we still are assuming that the data set is linearly separable, which may be unrealistic. We'll discuss how to get rid of that in the next lecture on soft margin SVMs. Good. Now, yeah, one thing that I want to mention is this might seem kind of familiar in terms of our perspective on regularization. Remember that regularization, we looked at this when we were talking about least squares or linear regression. I don't know how to spell these words. Okay, that's close enough. You know how to spell regularization. I'm not gonna. Okay, but anyway, the idea is that we somehow, when we're doing regularization in least squares, we essentially tried to optimize some loss function, and then additionally tried to minimize the magnitude of the parameter vector. That's kind of what we're trying to do here, in the sense that we're trying to optimize some function, which is kind of like this. And then this is a function of our data. And then also among the possible valid solutions, we pick the single one which has the minimum value of some parameter vector. So it's very much akin to how we did ridge regression, where you penalize based on the magnitude of the parameter vector. Good. And this will become even more explicit when we move on to soft margin SVMs, because it's the fact that it'll be very clearly related to that, where we'll have a sum of two different terms. But that'll be in the next lecture. So, but just recall that regularization plays a key role in kind of how we do SVMs. The last thing I'll mention is that how do we optimize these? Like, how do you solve the solution to this? Well, for this lecture at least, let me just say that it is possible, and there's some kind of nice things here. The fact that this is going to be, it's a strongly convex loss function. There's going to be, in fact, I believe, a unique minimizer for this objective function. And that's good, but we're not going to talk much about how to optimize it for today's lecture, because we're going to talk next time about soft margin SVMs, which will be more general, and any algorithm there also works here as well. So good. So far, we've talked about what the hard margin support vector machine problem is, how it differs from perceptron. It's kind of a stronger solution concept than a perceptron, and how we derive it and how we write it. So this is the optimization problem. In pretty much the remainder of this lecture, we're going to talk about a very important concept known as Lagrangian duality. So the gist of what this is going to say is that every optimization problem, this is a nice, perfectly fine optimization problem, but it's not always the easiest to solve for various reasons. And sometimes by looking at another equivalent optimization problem, this can be useful for getting insight into what's going on in the problem, maybe solving it a bit easier, stuff like that. But definitely there's a very beautiful duality that's going on, which will give us additional insights into the problem, which I think are very, very interesting, and tells us a little bit more about the geometric picture of what's going on with this parameter vector W and what it looks like. Good. So like I said, Lagrangian duality. Now this is going to get a little bit more mathematical, I'm going to warn you now, but I think this is a very important concept, and If there's one thing I wished I had earlier in my machine learning education, it was that I paid more attention to this sort of thing and really understood it, because I think this is a very powerful concept. So please don't skip over the derivation or just ignore it. Try to follow what we're doing, and I'll try to be give as much intuition or idea as possible as to why we're doing each step. So the Lagrangian dual is going to be an alternate way of representing any optimization problem. And like I said, it's going to sometimes have some advantages for various reasons. So let's see how we do this. Now, I'm going to sort of describe the steps. I'm not going to justify all of them, but we'll kind of see what we do. So let's start with this optimization problem. This is the core. This is what is known as the. Let me put the box around again. Oh. Right. So this right here is what is known as the primal optimization problem. It's going to be primal as opposed to the dual problem, which is what we are going to convert it to. So now, what we do when we are doing creating the dual is there's a series of steps. It's very mechanical, but the first step is, if you remember Lagrange multipliers, perhaps from multivariate calculus, the first thing we do is we start with each of these constraints, the things that are sort of hard constraints, that don't appear in the optimization problem. And what we do is we put a dual variable, kind of a Lagrange multipliers, and put them into the optimization function. So let me write this out, and hopefully it'll be more clear what I'm saying. So we start with this min over w and b. But then what we do is we say max over some parameter vector alpha, which is going to be non-negative. And we have the following. We have our old optimization function, the L2 norm of the parameter vector squared. But then we add on the kind of these constraints in the following way. We do, sorry, it's going to be the following, minus summation over I, alpha I times yi, and then basically the rest of this. Minus 1. So essentially we just moved this over to the other side, this 1 over to the other side, and we get this expression right here, and we put it here. And then we essentially just multiply it by this parameter alpha I, and we do this, we do this for every, and we put in the objective function, and in fact we do this for every single point or every single constraint in the data set. Or sorry, let me say this again. We take each one of these constraints that we have here, which appear in the original optimization problem, and for each of them, we make it so that it's written in the form something is greater than 0, greater than or equal to 0. We multiply it by a sort of what's known as a dual variable, alpha I, and then we add it to the we subtract it from the optimization function. And we do this for all of these constraints, and so we'll have a summation over all possible things. So that is this is the first step in taking the dual. Now, let me note that we've now got two different optimization problems here. We have to solve one inside the other. So these variables here, which we had before, these are called the primal variables. And this alpha that we introduced, this is going to be a vector. This is in particular going to be in r to the n. So this is going to be in r to the n. And it's basically going to be a size of the number of different constraints we have, which are one for each data point. And this is called a dual variable. We have primal variables and dual variables. Now, what we're going to do is we're going to swap the order of this min and the max. So this is kind of not something you can do in general. Let me say that, okay, so this is equal. These two problems are actually equivalent to each other. The values are going to be equal. Now, the next thing, like I said, we're going to swap the order of the min and the max. Now, in general, if you have a min and then a max problem, or a max and a min problem, you can't in general swap the order of the two and expect to have the same value. Doing the two in a different order might give you a different value. But in certain technical conditions, which in fact apply here, which we're not going to get into, you can swap the order of the min and the max, and it will maintain the same optimization, or the same value. So max, min, this, and we're just going to copy this right here. So this is exploiting something that is known as strong duality. And strong duality means essentially you can swap the min and the max, and the value will be equal. This applies only in certain settings, and it applies here for reasons I'm not going to get into. But if you care, you can look up things like Slater's condition. These are things which tell you when you can do the swapping and maintain the same value. But okay, good. We have done this. And now the cool thing is that we can actually now try to simplify this optimization problem by first solving the internal optimization problem. Like if you just ignore these alpha, consider these to be some fixed things, and you try to solve this minimization problem for any sort of fixed parameter vector alpha, we know exactly how to do that, right? If you just look at this term right here, this is just an unconstrained optimization problem, and we know how to minimize this just by taking the gradients and setting it equal to 0. So if you find the points where you take the gradient of this expression, set equal to 0, and if those conditions are satisfied, then this will be at a minimum, and we can actually eliminate this minimum. So we're just going to kind of ignore this for now and solve this as if it was just another optimization problem. So let's see how we would do this. Well, we just take the gradient. We take the derivative as normal. Let's start with the easier one. So this expression here, I'm just going to leave out the expression, but I'm going to write the partial of this expression with respect to, let's start with b, because that's a bit easier. And you can see that just sort of doing this very casually, you can see that in terms of the b is very easy to take a derivative with respect to, because it's just multiplied by alpha I and yi. So therefore, it's easy to just see by not even using vector calculus or anything. You can just see that this is going to be equal to minus summation over I alpha I yi. So that's the derivative, the partial with respect to b. And the one with respect to w is a little bit trickier. You'll have to take a gradient. You can use the claim that I made in a previous lecture to derive this, but also just being careful and looking at it carefully, you can see that the gradient of this whole expression with respect to w is going to be the following. First off, you have this term right here just becomes a w, and this term you can see that you're multiplying w by xi, yi, and alpha I. So if you do it out, then you'll see that this actually becomes just something very simple, just summation of alpha I, yi, xi over I. And recall that these are going to be scalars, but this is going to be a vector, and so we're summing up a bunch of vectors. The dimensions check out. Okay, so now, like I said, we're going to take the partials with respect to each of these things. And what did I say? We're going to try to minimize this as an optimization problem. And when we're optimizing it, what we do is we set the things equal to 0. That implies we're at an optimal, this is necessary and sufficient, I guess, if we're looking at a convex problem for optimality. But yeah, essentially, we're going to try to find a point where all of these are equal to 0. Now what do we do with this? The idea is, based on these, we want to get rid of this w and b, because we know which w and b will really optimize things. So what we're going to do is we're going to try to substitute these conditions back into this. Now, a first one we can start with is, for a first observation we can make is just by rearranging this. This actually gives us an expression for w in terms of the alpha i's, yi's, and xi's. So we're going to be able to eliminate w as a result of this. It's going to be summation over I, alpha I, yi xi. So that's another expression which we're going to use for w. Yeah, so now we're going to try to rewrite this expression now, substituting these things in. So let's start again, max over alpha. So kind of going from here to here. Yeah, going from here to here. This will be equal to maximum over alpha greater than or equal to 0. And now we're going to substitute in this expression for w. Let me write it a bit bigger. So that's the first term. Now the second term, let's try to expand it out a bit, just because it'll be a bit easier to see. So the first thing that we're going to do is we're going to take this summation alpha I and then multiply out this first term. So I just want to get rid of the ones and get it out here. So that'll give us summation over I of alpha I. So that's getting rid of this one. So the next thing we're going to do is going to take this minus alpha I times this b. So this gives us minus summation. Sorry, it's not exactly that. It's minus alpha I times yi times b. Notice all of these are multiplied by each other. So this gives us minus alpha I yi b. Now, the nice thing we can do here is notice one of the other conditions we said is that summation of alpha I times yi is going to be equal to 0. So even if it's multiplied by b, that's still fine. This overall summation is still going to just be 0. So we can use this expression right here, this sort of condition that we had, because again, we were trying to minimize it, to say that, okay, this term is always going to be 0 when we're at this true min. So we can just eliminate that, which is nice because this is getting already to be kind of complicated. Now the last term that we're going to look at is right here. So let's do this in perhaps 2 steps. So first of all, we have that this is minus, we've gotten rid of everything else. So we're going to have minus alpha I, yi, w, and inner product of wi, xi. So this is going to be minus summation alpha I times yi times inner product of w, comma, xi. Now, again, remember that we substituted in this expression for w, and we'll do that again to substitute it in right here. So this term right here, this can actually be rewritten in the following way, just substituting in w. This will be minus summation of, let me write in some of these indices to be more careful. Now, it turns out, if you think about it, this can be rewritten as the following, just substituting in this expression for w. And let me just write it. Actually, yeah, times. Maybe you generally put the scalars on the front, but let me put them here just because I've written myself into a corner. So let me try to explain this. What have we done? We essentially just took this dot product here and substituted in this expression for w, which does it here. And now this the dot product can also be written as this w transpose times x. So these two terms here represent the dot product. And the other thing, yeah, the other part is essentially the rest of it. This alpha and y are just multiplying it. And now the nice thing is, if you think about this, this is actually exactly this is exactly the L2 norm, because why is this? Because this is a linear operator, you can pull this out of the whole thing. So this is equal to minus summation over alpha I. Oh, sorry, let me note that this should be j. I chained the indices just to match up so that we don't get them confused. We have alpha j, yj, xj, transpose summation over j times summation over I of the same thing, alpha I, y I, xi. Sorry, it's getting a bit sloppy here, but essentially these are just the same thing. And now overall, this whole thing, this whole expression right here, can be written as the negative of the L2 norm of the same vector, because it's just a vector with the dot product with itself. It's just its L2 norm squared. Summation over I, and L2 norm squared. So this is nice. This was make sure you follow all of these steps, because this is kind of an important way to simplify it. But in the end, this is nice because of the fact that this term matches with this term right here, in the sense that they're the same, just with a different coefficient in front. So this is 1/2 minus 1. So putting those together, we're going to get that it's just going to be minus 1/2. So let me write that as the following. So with all these changes in place, let me sort of partition off this part. This can be written as max over alpha greater than 0 of minus 1/2 the L2 norm of this vector, L2 norm squared, plus summation over I of alpha I. So yeah, don't get these two I indices confused. These are sort of separate summation. That said, we still have one more constraint here. We still have the constraint that we have to have that's such that we have that summation of alpha I, yi is equal to 0. So this is the optimization problem. Note that this constraint here doesn't have to be there, because we've already eliminated this w, so it doesn't really make any sense to say w minus whatever. This is just basically a substitution, so it's done. But we still have this constraint, which is present. And the final thing we're going to do to simplify this as well, one last step, is going to change this from a max to a min, because generally we like to focus on convex minimization problems rather than concave maximization problems. So this essentially just can be changed to minimize over alpha greater than or equal 0, and you just negate it. So it'll be 1/2. Let me write this out actually a different way, which is going to be convenient for some interpretation. So we're going to do summation over I, summation over j, alpha I, alpha j, yi, yj, and then the inner product of xi and xj, and then minus summation of alpha i's. And once again, we still have the constraint that's such that summation over alpha I, yi is equal to 0. So this, at long last, we've done a lot of work, but this in the end is the dual of the optimization problem. So yeah, remember earlier we had this primal here. Well, it turns out that this optimization problem down here, the dual, is pretty much is exactly equivalent to the original. It just gives a different way of looking at the problem, which sometimes is good because you can optimize it in different ways, and sometimes because it is it's easier to solve in some ways, or it gives you a new geometric perspective on what's going on. So please make sure you try to follow all the steps, and if you have any questions, please ask to make sure they're clear, because I think this is an important concept which unfortunately people I think tend to skip over because it gets into some calculations, but it's important, so please try to understand it. Okay, so let's try to talk about this dual and see what is nice about it. I told you there's some reasons which is nice, and let me try to justify that for you. So one of the first things I'm going to tell you about, which I'm not actually going to justify, is going to be a bit mysterious for now, but one thing I want to tell you about is the fact that note that when you're doing this optimization problem, it does not specifically depend on the xi's themselves, but it only depends on the dot product of the xi's. Note that it doesn't actually use you can see the only place in the optimization problem where the x's appear is right like this, where it ends up being taken as a dot product with another vector. So that means I don't actually have to tell you each of the n by d vectors. There's n vectors, each of each in d dimensions. So in the way you traditionally receive the data set is by getting those n by that n by d data set. But here it only requires the dot product. So in fact, I could actually not give you the data set at all. I could just tell you the dot product of each pair of vectors, which would be an n by n data set. So for certain reasons, which we'll get into 2 lectures from now, this might be a good representation. In particular, say if D is very, very large, then it might be better to, in fact, just deal with this dot product representation of the xi's. And it might be more convenient if somebody gives the data to you in that format, just telling you the inner products. So that's an interesting feature, which might be a bit mysterious for now, but we'll revisit in a few lectures. Okay, what else is nice that we can say here? So we talked about like Lagrangian duality, and when we talk about Lagrangian duality, we actually have there's some properties which are nice, which apply, and there's something called, which you'll hear this term a lot when you're doing optimization, but something's called the Kkt conditions. And these are necessary conditions for optimality. So what do we mean by necessary conditions for optimality? I mean that suppose we solve the problem, either the primal or the dual, either one of these problems, if we have an optimal solution to it, then any solution that we have will satisfy 4 different conditions. That says if we optimize this, then there's some nice properties which we'll be able to get out of our solution. And one of the key interpretations when doing SVMs will pop out of this very nicely. So these are the following. I'd say 2 or 3 of them. 3 of them are kind of like obvious based on how we did things. But yeah, we'll see. So one thing is, the first one is a primal feasibility. And the second one is going to be dual feasibility. And what do these mean? I'll say in a sec. So primal and dual feasibility means that we're going to have that the primal variables and the dual variables are feasible. That means they're valid and allowed. They satisfy all the constraints required by both the primal problem and the dual problem. So essentially, of course, you have to, if you have a optimal solution, then of course it has to be feasible in both the primal and the dual, because otherwise it wouldn't even be a valid solution. Cool. So those are kind of uninteresting and maybe a little bit obvious. The next condition is stationarity. And very roughly speaking, what this means is essentially, it's essentially the type of thing by setting these derivatives equal to 0. Like essentially, it says that it's necessary that these being equal to 0 is going to hold. So just to draw a box, like these are kind of the stationarity conditions that we have here. So this is kind of also a little bit obvious in the sense that whenever this is kind of the equivalent of what we called Fermat's condition, which says that if we have an optimum, then we're going to be at a stationary point. So this should be nothing new to you in the sense that it's again just saying, okay, the derivatives, if we're at an optimum, then the derivatives have to be equal to 0. That's hopefully natural. So we're not going to worry about too much about that. But the important one, which will be key to our understanding here in our discussion is going to be that of what's known as complementary slackness, which is a bit of a fancy word. But what this means is the following. Essentially, what it means is that each of these individual constraints is going to be equal to 0. So let me copy paste this. So in general, it could be something different in the sense that it's whatever conditions you added into your optimization function. But at least I'll just discuss this for our setting. Complementary slackness for our setting means that for all I, we have that this term is equal to 0. So for every point we have, these two things to be equal to 0, their product. So I'm not going to justify why this holds, but this is a property that you will have for any optimal solution in this type of setting. So now let's suppose we have this property. Now some very beautiful things will come out of this in terms of how we can interpret the problem. And the first, and it'll come out of a very simple observation. If we know that this product is equal to 0 for each I, that means we have this following either thing, either or. So either alpha I is equal to 0, or let me write it as follows: yi hat. Remember earlier I denoted this term here as yi hat is -1 is equal to 0, because we have a product of two things. So one of them must be 0, or we could have both, or both. So why is this nice? Because it will tell us the value of the dual variables in terms of a very nice geometric picture. So what does it mean when 1 minus yi times yi hat is equal to 0? Yeah, when we have this condition satisfied. So that let's draw the picture we had before. So let's draw some points. Say something like so this is perhaps our data set. And what is our SVM solution going to look like? It's going to look something like this, maybe. And what does it mean by this 1 minus yi hat equals 0? Well, recall that we're going to have some sort of margin. So this margin is a distance from the line to the nearest point. So we can even draw what the margins are going to look like with some other colors. So let me draw it like, I don't know which color. Let's draw it in red, perhaps. So it will look something like this. This is not a perfect. These should all be parallel to each other. If I drew this perfectly, I didn't. But so okay, this is like one margin, and this is another margin is over here. So these are the lines which are at distance equal to the margin. So this is a picture of what it might look like. And this tells us that when we're looking at the alpha i's for each individual point, remember that there's going to be an alpha I for each point in our data set. Either it's going to be 0, or the point is going to lie on the margin. So let me try to point out some of these things to you. So for the kind of interpretation we can have here is that for these 4 points, this one is going to have alpha I equal to 0. For this one, and why is that? Because when we take this product yi times yi hat minus 1, this is not going to be 0, because geometrically that means that it's lying on this margin right here. So therefore, this one must be 0. This one, similarly, for very similar reasons, is going to be 0. This one is going to be 0, and so on. And the reason is because of these complementary slackness conditions, all of these have to be 0. Now, on the other hand, these ones, the ones which actually lie on the margin, these ones may be 0, but they may not be. So these ones, for this one, alpha I is greater than or equal to 0. It could also be 0 as well, but it may be non-zero. This one, alpha I is greater than or equal to 0, and so on. So you can see this gives us a very interesting geometric picture in terms of how the dual solution relates to where the points lie in space. The alpha i's, which are the dual variables, are going to tell us, are going to only be non-zero for the points which are going to be on this margin. And why is this useful, or why is this nice? Well, let me recall the fact that we could write our solution vector in the primal space, which is maybe more familiar to you, the W vector, as summation of alpha I, yi, xi. Now, the nice thing is, if these terms are going to be 0, if the alpha i's for certain points are going to be 0, that means they're going to totally disappear from this. Those terms are just going to be 0. And in fact, this can be written as a sum over all the I, such that alpha I is going to be greater than 0. So in other words, while we might have a very big data set with n elements, in fact, the number of points which lie on this margin is often and likely going to be much, much smaller. And the really beautiful thing is the fact that we can write the optimal solution to this optimization problem of the SVM as a linear combination of these points which lie on the margin, and maybe even fewer than them. So these points, there's a very important term for these points which have alpha I greater than 0. So if alpha I is greater than 0, strictly greater than 0, then xi, I guess, xi, yi, let's say xi, is a support vector. So that's finally where the name comes from. What is a support vector? Yeah, and the point is that you can write the solution, the optimal solution to your hard SVM optimization problem as a linear combination of these support vectors. That is, the points which have these alpha i's greater than or equal to 0. And so that means that there's often while in general this looks like it could be a very dense representation in the sense you're taking a linear combination of your entire data set, you can write it as a simple sum. And that's nice because it also tells you, for example, that if you just get rid of some of these points which are further, then they don't change the solution at all. Really, the only ones that really matter are those points which happen to be support vectors. Good. So is there anything else I want to say? Yeah, not really. That's about it for today's lecture on hard margin SVMs. Yeah, you can see that we covered a lot of stuff. First of all, how this compares with perceptron, how to go from the that it tries to maximize the margin, how to convert from a primal solution to a dual solution, rather a primal optimization problem to a dual optimization problem, and then from there, what type of things we can interpret using the Kkt conditions in order to get some nice geometric interpretations and discover what exactly the support vectors are. So these are going to be crucial concepts, and we're going to expand upon this in the next lecture, where we go on from the hard margin SVM and generalize this even further to the soft margin SVM. So just to give you a bit of spoilers for what's coming up, essentially you can see that this is the thing that's perhaps not realistic about hard margin SVMs, is they require us to have the data set be linearly separable. Soft margin SVMs are going to get rid of that and allow us to have things which cross over. So stay tuned for the next lecture for more on that.